Hello, everybody. This is our DoE project presentation. Our project is simulating atomic layer deposition using labels, flour salt, and temperature as the factors. Our group members are Anna Chang, Nolan Pham, Ichiro Son, and Jarek Stricker. In our project, we're going to briefly explain what ALD is, give you a high-level objective of what our experiment is and how the factorial design is set up, go into some details on the fabrication and the measurement process, and then we will do data analysis and our conclusion. So atomic layer deposition, or ALD, is a process in which single thin films can be deposited onto a substrate layer by layer at the atomic scale. It's good because it has precise control over thickness uniformity on complex surfaces, and it's getting popular in manufacturing currently. So with this project, we decided to try and understand what parts of ALD process are important to contributing to precise deposition control. Our small-scale experiment is a 2x3 factorial design with 2 replicates each. The control factors are label thickness, which represents film growth for the layers already deposited, material, which represents particle size, and the preparation temperature of the material, which represents deposition energy. Our response variable is going to be mass retained on the labels.
Three factors are label thickness with a high of 10 millimeters and a low of 5 millimeters, particle size with a high of salt particle size and a low of flour particle size, and temperature with a high of 10 seconds, a high power setting inside the microwave, and a low of no microwave exposure at all. Fabrication. The instrument that we use to measure the mass of each of the labels is a Cole Palmer 100 series scale with a resolution of 0.001 grams. The list of materials include self-adhesive labels with dimensions 76.2 by 50.8 millimeters with 5 and 10 millimeters in thickness. All-purpose flour, iodized salt, 2 flat ceramic plates, my phone's digital timer, and a Sunbeam 1400 watts microwave. For procedures, we randomly selected 8 labels for each of the 2 thickness and labeled the front of each label with appropriate factor combination. Measurement processes: scoop 8 ounces each of flour and salt on 2 separate plates and level flat with a spatula. For temperature high, place plate with flour inside the microwave at high power setting for 10 seconds. One at a time, remove that paper from the 2 labels marked high temperature flour and gently place face up on plate with flour. Wait 5 seconds. Immediately, weigh each label and record its mass on a spreadsheet. Make sure to clean the surface after each measurement. Repeat the steps 1 to 3, plate with salt and using the labels marked high temperature salt. For temperature low, repeat the steps 2 to 3 for low temperature label set.
The most dominant influencing factor is the factor A, and steep slopes in the main effect pot, and its statistical significance in ANOVA confirms that label thickness A is the most influential factor. And factor B, which is the particle size, is the borderline. And factor C is the temperature, which is the minimum impact that we could ignore based on the statistical evidence. The interactions A and B may warrant further exploration, given the visual trend of the steep slope of B, whereas the interaction of A and C or B and C appear to be minimum effect, and we have no reason to proceed on the analysis on those 2 interactions. Data analysis for variance. The label thickness A has the most influential factor, as p-value has the most significant, which is supported by the largest F statistics. And p-value for B is against the borderline at the value of 0.068, which is greater than 0.05. So it's close to 0.05, but it's still borderline. And factor C, which is temperature, the p-value is 0.276, and therefore it's not statistically significant. Data analysis, regression modeling. The surface plot shows the smooth surface, indicating a lack of or no presence of sharp peaks or deep crevice, indicating a strong linear relationship of factor A and B against the response variable, which is also supported by the fact that contour plot matches well with the surface plot.
So for our residual analysis, we produce a normal probability plot, a residual versus order plot, and a residual versus fit plot. On the left, the normal probability plot adheres relatively closely to our predicted linear line, so the residual distribution can be assumed to be normal. It should also be noted that the points on the plot seem to be evenly spread across the y-axis instead of gathering around the 50% mark, so the data is more data is required to make a conclusion about the overall distribution. On the right, no noticeable patterns are observed on the order plot, So we can assume that the order of the experiment was that the experiment was performed in had no effect on the residual. On this slide, we have a residual versus fit plot as well as a plot for each of the factors. Among all these 4 plots, there doesn't seem to be any emerging patterns or noticeable outliers on them, so we can assume that there is an even variation in the residuals between each of the factors. Next plot, please. In conclusion, our 2 to the third atomic weighted deposition experiment shows that label thickness and particle size were the most significant factors in the change of mass, with label thickness being the most dominant. As such, this experiment suggests the importance of surface preparation over the deposition process in ADLD. Reviewing our experiment, we noticed some improvements that could have made this process a lot better, such as having a more definite way to control our temperature and measure that temperature, as well as using different materials to simulate different surfaces and allowing us to encompass a larger range of situations. This is our reference slide, and thank you for listening to our presentation.